Good morning. My name is Pierluigi Siano from the University of Salerno in Italy, and I'm very happy to present this keynote at the 13th International Conference on Power System Technology, PowerCon. And I'm grateful to the organizers for inviting me, in particular to Professor Eding. Today I'm going to present the keynote that read a distributed parallel optimization for energy communities. In this presentation, after introducing the benefits of energy communities and the procurement of flexibility resources in the ancillary services market, I will present an architecture for the large-scale aggregation of prosumers that we have designed and developed at the University of Salerno in the context of an Italian pilot project to allow a community of prosumers to participate in the ancillary services market for providing flexibility, solving day-ahead and real-time optimization. Then I will describe an innovative distributed parallelized linear programming-based optimization that is scalable and privacy-preserving, allowing to deal with hundreds of thousands of prosumers without disclosing their information. I will also present some results based on a real Italian pilot project. And finally, I will present some findings and conclusions. As known in the smart grid, prosumers can aggregate in the so-called energy communities managed by an energy community manager that are based on the exchange of bidirectional flows of energy and on peer-to-peer exchanges to achieve self-consumption of renewable energy and to provide services to the power system. By participating in an energy community, prosumers may take a leading role in the energy transition and improve their economic convenience and comfort, while contributing to the grid efficiency and stability. Prosumers in an energy community can improve the exploitation of renewable energy produced inside the community by maximizing renewable energy self-consumption, thus reducing energy costs. These benefits can be further improved by carrying out peer-to-peer electrical energy exchanges inside the community. These activities allow them to achieve economic benefits, but also there are other drivers of energy communities that consist of flexibility potentiality, mainly based on some flexibility sources, including demand response, energy storage systems, and the electrical vehicles in the community. In fact, by contributing to the provision of ancillary services to the transmission or to the distribution system operator, energy communities may increase their economic benefits. Accordingly, we have proposed a new model for the provision of ancillary services to the transmission system operator that takes into account the flexibility, the energy flexibility furnished by new distributed resources such as dispersed and small generators, also based on renewable energy sources and frequently endowed with small batteries. Battery storage projects are becoming, in fact, more competitive in the last years if compared to other investment in the restriction of the electrical power systems, including, for example, investment for building new power lines or to power transformers. This is mainly due to the decrease of the battery cost. In particular, Distributed battery energy storage systems, also of small scale, that were mainly used to decrease the uncertainty due to renewable energy sources and to increase the energy self-consumption for the end users, can be also managed to provide energy flexibility to the transmission system operator. Considering this new model, and in order to exploit the potential of energy flexibility offered by new resources, the European regulatory framework has opened the ancillary services market to distributed energy resources, including energy storage systems and demand response providers. Among distributed energy resources, um, battery energy storage systems have gained recently more attention, mainly for their high ramp rate and fast response. The proposed methods consider both the planning and the real-time sessions to respectively define the unit commitment and the real-time sessions and the activation in the real-time session of the flexibility resources according to the Italian ancillary services market. Considering a pay-as-bid mechanism and a settlement period of 15 minutes, an aggregator or energy community manager, after carrying out a day-ahead optimization based on the day-ahead forecast, can offer services of flexibility in the up or down mode during the planning session, considering its baseline as a reference. If these offers are accepted by the transmission system operator, it can ask the aggregator or energy community manager to deliver the flexibility provision during the real-time session. If the energy in the real-time session is not delivered, an imbalance cost is applied. So the energy community manager should carry out a real-time optimization based on short-term forecasts in order to not pay the imbalance cost. It is worth noting that in also the Italian Regulatory Authority for Energy, Networks and Environment implemented recently a new regulation that allowed aggregated distributed energy resources to participate in the market for ancillary services. According to this new regulation, an aggregate or energy community can be composed of different types of resources, including generators, electrical loads, battery energy storage systems, electrical vehicles, and there is no limit to the rated power of a single resource, but we have that the overall minimum regulating power should be of 1 megawatt. So this is a global constraint that we need to consider. In order to implement the distributed parallel optimization and allow the exchange of energy data among all the prosumers, distributed intelligent devices based on information and communication technologies should be used. It is assumed that all prosumers are endowed with a home device gateway, smart meter, and an energy management system that is implemented on a hardware devices such as a Raspberry platform, a management system platform based on information communication technology infrastructure and software applications is also required for evaluating the absorbed and injected active power for all prosumers, the exchanging information between prosumers, and for managing all the batteries. The considered large-scale aggregation of prosumers can be managed by using this layered architecture, shown in this figure, where each energy management system can perform a local optimization. The layered architecture consists of a physical layer and a virtual layer that is essentially a virtual platform where all prosumers can access. The physical layer provides grid connection, smart metering, and communication to all prosumers. The virtual layer includes an energy information system allowing local site awareness based on real-time monitoring and on tools for the forecasting of photovoltaic production and load demand. By accessing to the virtual layer, prosumers can exchange only some privacy-preserving information related to their local optimal solutions and their power flexibility contributions to fulfill the global constraints of the global optimization problem I mentioned it before, that in Italy is 1 megawatt. The virtual layer is based on distributed ledger technology and on smart contracts to achieve both the real-time distributed parallel optimization while preserving the privacy of all prosumers. The considered approach is based on a pilot project that we are carrying out in Italy for the procurement of flexibility resources in the Italian ancillary services market. In the day-ahead optimization problem, the energy community manager aims at maximizing the remuneration due to the provision of energy flexibility in the ancillary services market, while minimizing the operating cost of the prosumers that are related to the cost of electrical energy. For up and down regulation, the global constraints related to the minimum power that the aggregator should provide are shown in these two equations, where the provided flexibility is related to the baseline of the aggregation that is calculated as the sum of the power profiles of the prosumers, considering that the batteries use a native control strategy for improving self-consumption. Some local constraints should be considered, including power balance for each residential prosumer, power limits from to the grid, power charging discharging speeds of the batteries. If the offer is accepted by the transmission system operator, the aggregator should guarantee the provision of an amount of energy flexibility in the time ranges defined by these discrete variables obtained by the AI optimization. And the following optimization problem should be solved, that is like the AI, but under some equality constraints that are related to the accepted power during the day ahead, and real-time optimization should be carried out every 15 minutes to update the control signals for the batteries to adapt to the changes of the photovoltaic productions and electrical loads of each prosumer, considering that the proposed parallel optimization is very fast. The discrete variables can be identified both in a centralized way by using a mixed integer linear programming optimization model, or in a heuristic way by using a new two-stage method based on hybrid variable neighborhood search and distributed parallel optimization. We decided to use the heuristic approach because the centralized formulation is not able to deal with extra large instances arising from real-world scenarios. By solving instead the problem in a heuristic way, we can achieve a distributed parallel framework in which all prosumers participate in solving the problem in a faster way, also keeping their information not disclosed. The way we accomplish this mission is by breaking down the centralized problem into many linear programming formulations and solving the resulting linear programming problems in a distributed parallelized way. A new distributed optimization method based on linear programming has been designed that overcomes previous methods based on integer and quadratic programming. The proposed method is scalable, allowing to deal with hundreds of thousands of prosumers in real time. It is privacy preserving. In fact, a global solution can be found without any prosumer knowing the behavior or objectives of any other one. It can be implemented by using the described architecture where each prosumer performs an optimization based on its specific objective function. As regards with the distributed parallelized linear programming based optimization, the idea is that of distributing the right hand side of the global constraint among all prosumers by using this equation in such a way so that the minimum power flexibility contribution of each prosumer is determined by the energy reserve available in its battery. And to solve this optimization problem, where the update of a vector gamma is achieved in the virtual layer by smart contract. The basic intuition behind this formulation is that we increase the weights of this vector gamma by a larger amount on those constraints which are more violated. Now I will present some results obtained by using this scalable privacy-preserving distributed parallel optimization method. More details can be found in this paper. If we consider, for example, a community, an energy community of 2,000 prosumers that should satisfy the flexibility constraints of 1 megawatt, we can see in this figure that the average power in a quarter of an hour of the absorbed power for the baseline, this dotted line, and in the case of up regulation in the month of June for both the centralized and distributed optimization, and we can see that the up regulation is delivered for 4 consecutive hours from 2 p.m. to 6 p.m. If compared to the centralized optimization, the proposed day-ahead parallelized distributed optimization can achieve the same flexibility in terms of delivered energy in the mentioned period and the same value for the objective function. Considering a day-ahead forecast error of 20% for electrical load and 10% for photovoltaic production, we can see in this figure the absorbed powers related to the day-ahead real-time optimization. It's worth noting that regardless of the forecast error, the parallel real-time optimization can achieve a power profile very close to that accepted during the day-ahead in the ancillary services market, thus not incurring in any penalty. As regards with the computational time, in this figure we can see that when considering the variable neighborhood search parallelized linear programming based optimization for day-ahead optimization by varying the number of prosumers in the month of June, for example, we can see that the proposed method is highly scalable, allowing to deal with hundreds or thousands of prosumers in a few seconds. Also, when considering real-time parallel optimization, the computational time varies between 13 and 25 milliseconds when considering different days during the year. Now let's move to the conclusions. I'd like to highlight that linear programming based parallelization enables not only to perform in an almost real-time way for very large scale real-world problems, but also to fulfill the privacy of prosumers. Both the real-time optimizations being highly scalable and able to protect the personal information of prosumers, overcome typical drawbacks of centralized methods. The proposed linear programming-based optimization methods can be easily coded up and implemented on microcontrollers and connected to the implemented layer architecture. Here there is a list for further selected readings on this topic. Thank you very much for your interest and attention. If anyone likes more information or ask question, please feel free to contact me by email.